All right, can everyone see this? Sweet. Awesome. Okay, well, welcome to the Software Demo Days series. My name is Megan Anderson. I'm part of the primer team here at Sandia, and our DOE program manager is Swara. Swara, would you like to say a few words about this series before we jump into MoorDyn today?
Yeah, of course, Megan. Thank you so much. And yeah, everyone, welcome to another installment of Software Demo Days. If you've been here before, you know the deal. We're here to foster cross collaboration between various different software developers of the software that we at WPTO provide funding for, and really just in general hope to lift up and create a more innovative space, an even more innovative space for the marine energy field. And yeah, I'm really excited today to learn more about MoorDyn, this mooring technology that can be used in a variety of applications. And, it accounts for the hydrodynamics of the system, allowing for nonlinear stress strain curves and so much more. And I just can't wait for y'all to learn more about it. And yeah, let's just get on with it. I'm really excited.
Great, thank you. Right. So real quick, this is where we are in the series, and we started off a few weeks back in March with the primer kickoff. We hosted WEXIM in April, and we also hosted OpenFast last time. If you guys attended the session last time, you were interacting with the CoCalc platform, which is kind of shown by the demos in green are the ones that will be using CoCalc. So today we'll be using CoCalc for part of the MoorDyn demonstration, as well as the next demonstration and WECOP tool later in June. All right, so without further ado, I'll hand it off to Ryan from the MoorDyn team at NREL. And yeah, he's going to kick off the demo for us.
Great, thank you, Megan. Cool. Just want to make sure, can everyone see my screen?
Yes.
Awesome. Cool. Yeah, welcome everyone. I will be kind of talking through MoorDyn today, kind of what it's used for, what you can do with it, and hopefully we can have a good discussion afterwards about some potential next steps and collaborations that could use our software in the future. As I'm going through the presentation today, feel free to stop me at any point if you have questions or anything's not clear. This is kind of a back and forth, hopefully, so I don't want to just be talking to everyone the whole time if people are sitting on things that might be confusing. Just a little bit about me. I am probably two and a half years at NREL now. I'm a mooring modeling engineer, and kind of a lot of the work that I do is in MoorDyn development. And so, yeah, I'm excited to kind of walk everyone through the code today. So kind of right off the bat, let's get into what MoorDyn is. So MoorDyn is an efficient and versatile lumped mass mooring model that simulates mooring dynamics in the time domain. It is a library that's called by an external function or driver code. So it's really well set up to be coupled with other solvers. And we'll talk a little bit about that later. It's open source and it is ongoing continuous development and continuous improvement. So we're always working on it and adding new features. And it has two main versions. So there's MoorDyn C and MoorDyn F, and they're these kind of suffixes are related to the language they're written in. So MoorDyn C is written in C++, MoorDyn F is written in Fortran. The reason for the two versions is kind of long and convoluted, and we can get into it if you really want to, but in short, the MoorDyn F version is structured so that it fits really nicely into OpenFast and is a core mooring dynamics module inside of OpenFast. And MoorDyn C is kind of more flexible and able to couple with any code in a variety of languages. And MoorDyn C is also what is coupled with WEXIM for those familiar with that system. MoorDyn has a variety of wrappers that allow it to be used in a number of different languages, including MATLAB and Python, Rust, Fortran, C, C++, and also Simulink. So this allows some really nice couplings with kind of higher fidelity tools like OpenFOAM, for example. But there's a bunch of kind of different ways you can take things. So before I go too far, I want to give credit where credit is due here. So this is kind of the core MoorDyn development team. There's myself at NREL, who works on MoorDyn C and MoorDyn F. There's Matt Hall, who is kind of the original creator of MoorDyn, and still serves in a developer and advisory role on both the MoorDyn C code and the MoorDyn F code as well. And then also at NREL, we have Stein Hausner, who works on the MoorDyn F code more specifically. And then we have some industry developers as well. So we have Jose Luis Cercospita from Core Marine in Norway, who works on MoorDyn C. And we also have Alex Kinley, Kelson Marine in Maine, who works on MoorDyn C as well. So I'll get into some of the use cases now of why you'd want to use MoorDyn or kind of where it's a good tool. So it originally was developed as a mooring dynamics model for floating offshore wind turbines. So that's kind of its most famous use. And you can see, in the bottom right is a figure there that kind of shows what a MoorDyn simulation can look like and kind of the systems that you're able to simulate. This is kind of where you'll hear MoorDyn talked about the most, but it's not the only use of it. So MoorDyn also has the capability to simulate pretty much any device that's attached with mooring lines to the seabed. So kind of based on the success of MoorDyn as a mooring dynamics solver for floating offshore wind, there was a lot of interest in bringing it into the marine energy space. And so that's when kind of the MoorDyn WEXIM coupling was developed, and we really started modeling wave energy converters specifically. Some kind of cool projects with wave energy converters we've done. There's lots of WEXIM work out there, but NREL actually was also the development team behind the Stingray, the Sea Power Stingray mooring system. So some colleagues of mine actually went through and designed all the components from that, and MoorDyn was one of the tools they used kind of in that analysis process. You can see a little graphic of the Stingray WEC down here, and we were actually able to simulate the entire device, so including the structure at the waterline, all in MoorDyn. So it's kind of a cool, fun, unique application of it. MoorDyn can also be used in OpenFast, along with OpenFast's ability to simulate MHK turbines. So I'm sure for those who hopped on the call that Hannah led, talking through OpenFast, you were able to see kind of the RM1 floating example that she worked through, and that used MoorDyn, so it simulated the mooring lines of that device. So that's another kind of fun application and I think relevant to today's audience. A really unique feature of MoorDyn is that it has the ability to simulate arrays of devices or devices with shared moorings. So in floating offshore wind, we use a tool called FastFarm that uses MoorDyn, but we can also do this in WEXIM. So you can see here we have an array of point absorber WEX that are all using shared mooring lines. So that's kind of a fun application as well. A couple more edge cases I would say that MoorDyn's used for, but are nonetheless important. It's frequently been used for hybrid model testing. So this is where, say you wanted to test a system in a wave tank. The wave tank's not deep enough to simulate your real world environment. So you are able to set up MoorDyn to actuate a winch. And so MoorDyn basically actuates a winch that pulls on your device, and then the device effectively feels like it has a real mooring line attached to it in whatever water depth you choose. It's also used for simulating mooring systems in aquaculture. Kelp farms is a common one that we'll talk about. And then it's also kind of the engine under the hood for a number of different industry tools as well. And that's really a lot of what the MoorDyn C code is used for. So yeah, it's a kind of a wide-ranging and pretty versatile tool. It's not specific to any one technology, and I think that's why it's a pretty exciting thing to be presenting today to everyone, because I think we have a lot of different perspectives on the call. So I'll get into now some of the core capabilities of MoorDyn. So I think right off the bat, mooring lines, that's pretty obvious. We can simulate chain mooring lines, synthetic mooring lines, steel wire mooring lines. We can also simulate the dynamic power cables. So these are the offtake cables or the umbilicals, depending on how you want to call them. But we're able to do this basically by using these mooring lines, but giving them a non-zero bending stiffness so that they have a bit of rigidity to them as they try to flex. And this is a really useful tool when we're looking at designing systems to kind of extreme loads or whatever design cases are needed. Typically, the dynamic power cables constrain that, and so being able to examine the loads on the cables is really important. MoorDyn also has the ability to simulate floats and buoyancy elements and clump weights as well. So in the wave energy space, these are super important parts of a mooring system because they help reduce the vertical loads on the device. And that's one area where MoorDyn has been frequently used, is kind of simulating the RM3 device and some of the floats that exist in that mooring system. We also have the ability to simulate rigid body dynamics and surface piercing rods. So when I was talking about that Stingray WEC simulation we ran, we're able to effectively build the entire Stingray WEC out of rods and then attach that to a rigid body and be able to capture the kind of hydrodynamic forcing on the device and simulate how that would move in real sea states. We also have the ability to simulate water kinematics as well. So we're able to simulate waves and currents loading the mooring system, as well as any surface piercing objects like rods. Cool. So onto some additional capabilities that MoorDyn has that I think help it shine in a variety of different ways. I'll try to get through these pretty quick, but if anyone has questions, please stop and ask for more details. So MoorDyn has the ability to simulate viscoelastic synthetic mooring lines, and it has two ways to do this. You can either use a constant dynamic stiffness or a load-dependent dynamic stiffness, and this kind of gives some really nice insights into how a highly dynamic mooring system would move if it has synthetic lines. We also have the ability to input any sort of stress strain curve for the stiffness of a mooring line. And this allows us to simulate nonlinear springs, which have been used before as kind of a inline tool or technology that you put into the mooring system to help reduce loads. Another kind of fun feature that is frequently used is a line actuation of mooring. So this allows you to control the length of mooring lines at any given point in time. And this is, super useful if you're trying to simulate a active mooring system or a winch or something like that. We also have the ability to simulate highly dynamic bodies. And so this is kind of unique in the ways that it's not constrained by any small angles or any approximations like that. And so we're able to kind of simulate things that are really moving a lot at the waterline or underwater. And we've used this before for simulating things like buoyancy cans and some unique floating offshore wind applications. We also can simulate kind of interactions of the mooring line with the seabed. So we're able to input a bathymetry grid that allows us to have a non-uniform bathymetry across our entire simulation space. And then we also have seabed stiffness and damping and friction, which you can derive from soil properties and gives some really nice kind of more realistic estimates of what's going on when you have a case with a mooring line on the seabed. We're able to simulate mooring line failures as well. So at a predetermined point, when it reaches a tension threshold, we can have the mooring line fail. And then, this was kind of a really useful thing if you're looking at shared moorings or any sort of like array level system and looking how failures can propagate throughout the system and kind of how to respond to those. And then the last kind of newest feature of MoorDyn that I'd like to highlight is vortex-induced vibration modeling. So for those who aren't familiar, Vortex-induced vibration is kind of an oscillating force that occurs to a cylinder or a rigid cylinder when it's moved through a fluid or when a fluid moves over it. So we can simulate fluid flow with currents, with waves, and also with the motion of a device moving our cables and mooring lines through the water. And then we're able to simulate a VIV force that comes from that. And kind of what's really exciting with this is it's actually the only open source time domain VIV solver that at least we're aware of in the world today. So I think we're pretty excited about what new opportunities could come from that. Cool. So that's kind of how you use MoorDyn and what you can do with it. But how do you actually build a mooring system in MoorDyn? So to do that, you have kind of 4 key building blocks. You can think of them like Lego pieces that you use to assemble your system. So there's point objects, and these are kind of these general 3 degree of freedom objects that have they can have hydrodynamic properties, they can have volume, they can have mass, and so they can be used to approximate simple buoyancy modules, simple clump weights, and they're also kind of the key tool for connecting mooring lines to other things in your system. You also have line objects. So line objects are what the mooring lines are. They're made of effectively a bunch of lumped masses with spring damper pairs connecting the masses together. And then each of these lumped masses also approximates its hydrodynamics at a given point as a cylinder. And then together it kind of evolves the mooring line's dynamics throughout time and space. Like I mentioned earlier, these line objects can also be used to simulate dynamic power cables. And to do that, you just provide them a non-zero bending stiffness and then the appropriate elasticity and weight properties. The third object in MoorDyn that you can use is a rod object. So this is a rigid cylindrical object. It's effectively a line with infinite bending stiffness, right? So it's just a bunch of point masses all connected rigidly. The hydrodynamics are calculated the exact same way. So each point is a Morrison element that then can calculate hydrodynamics when you have surface piercing conditions where part of the rod may not be submerged. Unlike points, rods are a 6 degree freedom object, so they have a knowledge of both their position in space, but also their orientation. And because they're a 6 degree freedom object, they're actually able to pass bending moments from a line with bending stiffness into an object that they may be attached to. So this allows us to kind of really accurately simulate the hang-off points of dynamic cables and kind of what's going on at those points. The fourth object in MoorDyn is a body object. So a body is kind of, I think of it as like a scaffolding, right, that you can attach a bunch of things to. So it has its own unique properties that you can provide. You can give it a moment of inertia matrix. You can give it an added mass matrix, a drag coefficient matrix as well. But more than anything, you can attach points and rods to a body, and those points and rods will move rigidly as one. So in the case of that Stingray WEC that I talked about earlier, you're able to attach a bunch of rods to this body, and then the hydrodynamic forcing on the rods can get all added up at the body center, and then the dynamics of the entire system can be simulated. So bodies are super useful for simplifying kind of interfacing points of MoorDyn with an external code. So for each of these 4 objects, they can have a couple of different attachment types. They can either be a free object. So this is a object that's free to move in space. It has kind of no control over its kinematics other than the forces that are applied to it, and it will react accordingly. You can have attached objects. So these are objects that are attached to a higher order thing. So I think a common example would be a point attached to a body. So the kinematics of these attached objects are controlled by the parent object that they're attached to, and the forces that they feel are then passed on to the parent object. You can have coupled objects. So these are objects that are controlled by an outside program or your driver script. So these are either like points or bodies or rods that are passing their forces out to the script and then receiving kinematics from the script telling them how they move. So these are kind of the interfacing points that you use when you're working with MoorDyn. And then the last attachment type is called coupled pinned. And so this is only available for the 6 degree of freedom objects like rods or bodies, but it's a bit of a hybrid between coupled and free in that the translational degrees of freedom, so your X, Y, Z, are controlled by your external program, but your rotational degrees of freedom are free to move according to the forces they experience. And so this is kind of really useful in the case of like buoyancy cans, if you're trying to simulate how do things move about a joint when they're being kind of actuated at one end. In general, the way MoorDyn processes this information and evolves the model is kinematics move downwards from coupled objects to attached and then to free. And then the forces are returned upwards. So a general time step in MoorDyn would be an outside program tells MoorDyn where the system is in space and how fast it's moving. That information then works its way down through the system until it gets to the mooring lines. And then the forces on the system are calculated and they're worked back up until they are added together at the coupling points and passed back to the outside program. So that's kind of the building blocks you can work with and how they react with each other in MoorDyn. But how do you actually run the code? If you have all these system built and set up. There's 2 real ways to do this, and they both require an external driver script. You can either use an external solver. So this is where MoorDyn is interfacing with another model and telling the model what the mooring system is doing to the given system, and then the model tells MoorDyn what the system's doing to the mooring system. So like I said, the solver is going to pass in kinematics of coupled objects, and then MoorDyn is going to return the forces at those coupled objects. So it's kind of an easy interface back and forth, and the solver doesn't need to know anything about what's going on inside of the mooring system. Examples of this are Wexim and OpenFast. I think those are like the pretty common and famous examples, but there's also proprietary codes and individual solvers that other people have made. You can also run MoorDyn standalone. So this is where MoorDyn will compute the forces and kinematics of a user-defined system of free objects. So this has been done for simple buoys, kelp farms, and then also rigid platforms like that Stingray device I talked about earlier. So that's kind of the overview of all the pieces. Here's kind of how they fit together. And I know there's a lot here, so I'll work through kind of the main points separately, just so you can kind of visualize. Before I jump too far into that, let me just say that MoorDyn, the color coding here. So the light blue is kind of what you would interface with as a user. These are things that you would typically interact with. The green is the external solver that either you build or you are using, so if it's already set up. And then the other colors are just internals of MoorDyn that you don't really ever need to touch unless you're changing the code yourself. So to start off with, initialization. So you set up your mooring system in your MoorDyn input file. I can talk through that a bit more later. There's also some great descriptions of that in the MoorDyn documentation that you can check out. And in the MoorDyn input file, you may want to include other kind of sub-input files, and you list the file paths in that MoorDyn input file to these other input files. So it could be things like a bathymetry grid, it could define your water kinematics, it could be a nonlinear line stiffness curve that you want to include as well. And then the external solver also contributes to initialization. So the external solver tells MoorDyn at the start of the simulation, this is where your device is, and this is how fast it's moving. If you're using the C code, you can actually kind of extract that from the input file without having to do anything crazy. But all of that information gets passed into MoorDyn, and then it will initialize the system and solve for steady state. And I want to spend just a little bit of time on this initialization process because it's probably one of the most common questions we get about MoorDyn, is like, how does this work and what's going on? So your input file serves as your best guess of how you're setting up your mooring system. So you say, I think my buoy is going to be here. I think my clump weight's going to be here. There's a mooring line between them, but you don't have to get it perfect in that step. So once you kind of set up your input file, MoorDyn reads it. It places all the points on space, and then any place there's a mooring line, it tries to solve a simple catenary equation for that mooring line to kind of get a better estimate of how the mooring line will be hanging in space and how it will be stretched or not stretched. This routine will commonly fail, and people will commonly report, hey, I see this error message, what's going on? It doesn't mean that anything is wrong. It just means your initialization process will take longer. So once this catenary solver tries to kind of estimate where these curves are, then a relaxation process allows the system to effectively fall into equilibrium. So all the free objects in the system and all the mooring lines are just run through simulation with scale drag coefficients until the tensions in the mooring lines stop oscillating. And once they are below a certain threshold, then we just go ahead, consider the system initialized, and proceed with the simulation. This figure on the right here kind of shows you steps in that process. So this black line here is right after that catenary solver worked its magic. So you can see you have a point here and you have a point here. They're fixed in space. You can see the solver, tried to estimate a catenary line between some points. It wasn't able to here. It had a linear line, but it got a best guess of where things are. And then these red and blue lines indicate kind of two different relaxation routines that can be used. But you can see how they allow the system to kind of fall into a more natural state. And then once that state is reached, you can start your simulation. Cool. So once you've initialized your system, the next step is kind of to look at how your external solver is going to interact with your system. So you're going to have effectively a coupling time step. So this is the time interval between which your external solver will call MoorDyn. So at each call to MoorDyn, it's going to pass in the kinematics of all the coupled objects. MoorDyn is going to update those coupled kinematics, and then it's going to work through its internals for however long it needs to, until it reaches one time step advanced from when you called it with the solver. It'll then add the forces together and return them back to the solver, and then the solver can either output those forces or use them for its own iterations. So the MoorDyn internals themselves, there's a MoorDyn internal time step that is typically an order of magnitude smaller than the coupling time step. So if you're coupling at 0.1 seconds, then your MoorDyn internal time step would be 0.01 seconds. And what this means is it just means that MoorDyn's going to run more iterations inside of that time step before outputting the coupled forces. And it helps with numerical stability, but also with accuracy. So what MoorDyn will do is it'll take those coupled kinematics and it will pass those kinematics throughout the system. And then it will start iterating through all the free objects. So the mooring lines, the points, the bodies, the rods, whatever is a free object, it's going to set the position and velocity. It's going to compute the forces and find the acceleration that results from that velocity. And then it's going to integrate that acceleration to find velocity at the next time step. And it does the same with velocity being integrated to find position. And that way MoorDyn can kind of really quickly iterate through the entire system. And it's a super kind of functional and nice way to do this, and it allows us to easily add new forces and other new features without having to kind of restructure the entire code. Cool. So once you run your simulation, what do you do with the outputs? There's a couple options for how to look at what MoorDyn's done. There's the PyDat view tool that Hannah talked through in the OpenFast demonstration. This is kind of a Python-based tool that allows you to quickly open tab delimited files, like what MoorDyn produces, and then quickly visualize the output channels that MoorDyn has made. There's also support for ParaView. So ParaView can open VTK files and We have a couple of different ways you can write those. So OpenFast can write VTK files that can be read in ParaView. MoorDyn C has an API interface that you can use for writing these. And then Wexim also is able to write these with using MoorDyn. And so this kind of gives you some nice visualizations. The figure on the right here is actually the ParaView visualization of the MHK RM1 floating test from OpenFast that I'll talk through later today. There's also the tool MoorPy. So this is a quasi-static mooring model, but it also kind of has this unique side feature in that it can read MoorDyn output files and give you animations of your mooring system as well as just still images of your mooring system. And then Wexim is also set up to read MoorDyn output channels, very similar to how PyDatView is, and produce some plots. And I'll talk through that as well later. Yeah, so I guess the last thing I wanted to go over was just kind of pointing everyone to some resources. We have a documentation site for MoorDyn that's hyperlinked here, and these slides will be sent out later, so you'll have access to all these links. So yeah, there's the MoorDyn documentation. There's the NREL forum. So this is typically used for wind energy things, but there's also a decent amount of water power work on there as well. And it goes back quite a ways, so you're able to kind of look at a long history of responses to questions on how to use MoorDyn. Similar to that is the OpenFast repository issues page. There's a long history of MoorDyn answers on there as well that is worth checking out. And then more kind of on the newer side of things, but also well monitored, is the MoorDyn C issues page that I have linked here as well. So kind of all four of these are really good resources if you run into trouble. Also, always feel free just to send us an email. My email's up there and Matt's email is up there as well. We're more than happy to provide help that way as well. Cool. So we're going to jump into demo days examples now. So we're going to talk about running MoorDyn standalone, and we're going to use CoCalc for that. We're also going to look at running MoorDyn with OpenFast and then also with Wexim. But before we jump into that, I just wanted to kind of open up to any questions people may have about the presentation or MoorDyn specifics before we kind of jump into the examples. Cool. Sounds like not too many questions. So with that, I'm going to stop sharing here and I will share my my CoCalc screen. See, yep. And again, feel free to stop me at any point during this presentation here. I know there can be kind of certain parts that can be confusing. For those who aren't familiar, I'm in the MoorDyn directory of the CoCalc page. So I believe that all the everyone in the course here today should have access to that. So if you aren't able to access this directory and see these files, please speak up so that we aren't losing anyone here. Great. Okay. So for today's demonstration, we're going to be using the Visual Studio Code instance inside of CoCalc, and I think this provides a pretty nice environment for people to work with. So from the main CoCalc page here that you see, click on this VS Code button, and that's going to launch a new tab for you that will open a Visual Studio instance. And this is kind of a nice environment for working with code in general, and with working with what we're going to be doing today. For those who aren't familiar with the VS Code environment, I'll just give you a brief overview. So on this left side here, you have the File Explorer, and this shows you all of the files that we have available in our workspace. You'll see that these are the exact same files that are inside of this CoCalc environment as well. Then we have a couple of other things here, kind of some non-essential tools for what we're doing today. But let's start by opening up this MoorDyn standalone Jupyter notebook. So if you double click on that, you'll see it's here. It's not in italics or anything. And this will kind of give us an example of running MoorDyn standalone. For people whose first time this is opening up VS Code on CoCalc, you might get prompted to download some extensions that are for Jupyter. Go ahead and do that. Don't be kind of alarmed by any of those. The extensions that it suggested that I install are the ones right here. So hopefully you get prompted to do something very similar. Great, so I'm going to go back to my file explorer here, and then I'm going to go over and select the kernel that I want to be working with. So this just gives us access to kind of the MoorDyn set of tools. So once you hit select kernel, go ahead and hit Jupyter kernel here, and then in this search bar, search for MoorDyn. And once you do that, you should, in theory, get your MoorDyn environment. But I'm not seeing it here. Let's see.
Maybe try under Jupyter kernel.
Yeah, that's where I was looking. It seems to have disappeared.
Oh.
Any suggestions?
In my computer, if
Go ahead.
Jupyter kernel.
Yeah. Are other folks able to select the MoorDyn kernel?
Yes.
Mine was automatically selected.
Yeah, same.
Okay. Well, that's fine as long as it's working for other people. I can kind of walk through kind of what you'll see. So let's see here. Why don't, if I can't get this kernel to work, let's see. Here's what I'll do. I will just do the same demonstration files, but just running them locally on my computer. But they're all the same files that you'll be looking at. So hopefully we're able to kind of run through files together at the same time. So let's do this. Cool. So what we're looking at here is VS Code. The color scheme might be a little different, but it should be very similar to what you're seeing. So what we're going to want to do is kind of walk through running MoorDyn C using the Python interface that we're able to that it has. So kind of some notes before we get started. MoorDyn is a library. It's driven by an external code to some degree. The kind of most famous examples of this are Wexim and OpenFast, but there's a couple of other kind of private codes that are out there and people's own codes that they've built as well. For this demo, we're going to be using some examples from the MoorDyn C code that are in the MoorDyn documentation and the MoorDyn C kind of test library. For those who are interested in running the Fortran version of MoorDyn as a standalone code, I have a MoorDyn F example directory here. There's a README file in there that you can work with. It should produce the very similar results to what we're going to produce today. So yeah, no need to kind of worry about any changes there. So to get started, we're going to start by just importing the modules that we need. So we're going to run this cell here by pressing this little play button, and that's going to import MoorDyn. It's also going to import MoorPy, which is just a nice visualization tool. We don't need to kind of get into any more details about that. And then it's going to import the NumPy module, which is a nice tool to have as well. So for today's simple example, we're just going to be working on a 3-line catenary mooring system for a floating offshore wind turbine. I know this is a marine energy call, but this is kind of one of the most simple examples that we have set up for MoorDyn, and is kind of one of the first ones we point people to when they're trying to learn it. So you'll see here we have 3 mooring lines that are coming off of a platform, and they're attached to the seabed. They're attached to the platform about 70 meters below the water line and about 5.2 meters radially from the center of the device. This attachment point is called the fair lead. So for today, if you hear me talking about fair lead, all I mean is the point where the mooring line attaches to the device. To set up this system in MoorDyn, we have the following input file here. And this input file is the exact same as the lines.txt input file that you should see in your CoCalc directory. So how do we define this actual system, right? We have 3 mooring lines, it's attached to the platform and it's attached to the seabed, but like, how does that turn into a MoorDyn input file? So the way we do this is first we define a line type. So this is kind of the definition of the properties of the mooring line. So we're going to call this type main, and all that means is that's just an identifier that we can use later on for referencing what this type of line is. We give the mooring line a diameter, we give it a mass density, we give it a stiffness value, and then we give it a damping value. And this negative value is actually representing a fraction of critically damped, and where critically damped is targeting the natural frequencies that can typically be excited due to numerical instabilities. So a good value for this is typically -1 or something close to it. So today we'll use a -0.8. Then we have this EI value. So this is bending stiffness. Because we're not simulating a dynamic cable here and we're simulating chain, we'll just leave this as 0. And then we have some hydrodynamic coefficients as well. So CD is your drag coefficient. CA is your added mass. And then CD and CA ax are your axial coefficients for those. So this is kind of the coefficients along the length of the line. You can think of it as like the skin friction of the mooring line, for example. So once we define the properties of the mooring line, we go into defining the geometry of your mooring system. And for this, we use the point properties list. So we saw here we have 3 mooring lines, and each mooring line is attached at one end. So that gives us 6 attachments. And that's reflected here in this point list. So we have 3 fixed attachments that represent our anchors. You can see they're at -320 meters, so they're on the seabed. And they have no mass, no volume, and no hydrodynamic coefficients either, because we're using them to simulate just an attachment rather than something like a buoy or a clump weight. The other points we have are labeled as coupled, and that's where these mooring lines are going to attach to the device. So because they're labeled as coupled, that means for our simulation, we'll be telling MoorDyn how each of these 3 points are moving in space. And you can see those are also located 70 meters below the water line. Once we've defined our points and the geometry of our mooring system, we're then able to define how things are attached within the system. So this is where this line list comes in play. And this is where we define our actual mooring lines. So we say, okay, our first mooring line is of the type main, which is what we defined above. And it's attached at end A to point 1, which is this anchor point, and attached to end B to point 4, which is this fair lead that's coupled. And then we say the line is 900 meters long and has 20 segments. The number of segments is just how discretized your mooring line is. Typically 20 is a good number. It really depends on your depth, but you kind of want to aim for the 5 to 20 meter long segment range. That number can get bigger as you go to longer mooring lines. And then the last thing here is a flag that just tells MoorDyn to output the positions of all of the nodes or segments on the mooring line at any given time. Okay, so once we've defined our mooring system, we need to give MoorDyn some environmental parameters and some other kind of settings for how we want our simulation to rerun. I'll walk through kind of the key ones here. There's many things you can put in this option list, and they're described in the MoorDyn documentation. But just a few of the key ones, we have turned on the write log flag, which is going to write a log file for our simulation. We've also turned on the DT, or we've set our DTM, which is our mooring model time step, to 0.002 seconds. So this is that internal MoorDyn time step I talked about earlier. Then I'll just talk through kind of our initialization parameters that we have here, because this is a common kind of sticking point for people. So we have DTIC. So this is the time interval that MoorDyn will look for the tensions to be constant over before it considers it to be converged. So it says, okay, your tensions have to be constant for this amount of time before we're going to say it's converged. Tmax IC is the max amount of time MoorDyn's allowed to run for before it gives up on this initialization routine. So, if it's not able to find it in 100 seconds, go with your best guess and move on and start running your simulation. CD scale IC, that's your drag scaling coefficient. So that's the factor by which things are going to be scaled, and that'll help increase the hydrodynamic damping and hopefully allow you to converge on a tension threshold faster. And then we have this thresh IC flag, and this is kind of the percent difference that in tensions that it looks for. So the tension differences need to be under thresh IC for the duration of DTIC for it to be converged. The last kind of section here is the output section. So this tells MoorDyn what to write to the output file. Today, we're just going to have it write 3 simple channels, fair 10, 1, 2, and 3. And fair 10 is just the fair lead tension of the line number defined here. So fair 10, 1 is the tension at attachment point B. So first step is that we want to initialize our mooring system here. And so for today, what we're going to be doing is we're going to have MoorDyn create a mooring system with this system object here. And then we're going to set our initial positions of each of the points to be what we define them in the input file as. So you can see we have 5.2, 0, negative 70, and that corresponds to our first coupled point here, 5.2, 0, negative 70. So we do the same for all of the positions in the kind of input position vector. And then we want to make one of the velocities as well. So to start, we're going to say our system's not moving. And so we're going to have a 9 degrees of freedom times our times 0 here. So that's going to give us kind of a list of zeros that's 9 elements long. So once we have those 3 things set up, we can pass that into the MoorDyn initialization call. And if we click run this cell, you're going to see we get a bunch of information printed out here. So what this cell tells us is that MoorDyn has read in one type of a line. It has 6 points and it has 3 different lines, and we have 3 coupled points. So that's kind of hinting that, okay, we read our input file correctly and we have what we want. It's telling us that it's using a second order Runyakuta, which is the default time integrator in MoorDyn. There's a variety of different integration schemes you can use if you want to kind of get into those details. You see we have no water kinematics set up, and then it tells us that it's initializing the system. So if we click view scrollable element here, what you'll see is that you're able to look through, let me just move that out of the way. Yeah, you're able to look through the MoorDyn outputs, right? So, it has our system set up, and then it says, okay, here are the lines in your system. Here are their properties. That should match what we defined in our line list when we define that main type of mooring line. And then it tells us, okay, each of the lines initialized successfully. It looks like it initialized in 52 seconds. So well within that 100-second threshold that we gave it for initial condition generation. So once our system's initialized, we can get into time stepping. So what we're going to do here is we're going to run our simulation for 5 time steps with a velocity of 0.5 meters per second in the positive x direction. So this code here just sets the 0, the 3, and the 6 index of your velocity vector to 0.5. Ben, do you have a question?
Yeah, sorry, I've kind of follow along, but I've fallen off at some point. So my initialization field is blank. So did you populate it by running the earlier, like the input file?
So did you click run on this cell here?
Yeah, but no, you know, there's no code in the initialization, like little text box.
Like this cell doesn't exist for you.
Sorry to jump in, but yeah, I can jump in there and give you that code. We were just doing some last minutes of getting the notebooks configured and working properly. So thank you for putting that out so we can get that sorted.
Oh, okay, thank you. Yeah, I'm happy to copy it from the chat or whatever.
Yeah, I can jump into your notebook actually and help you there.
Thank you.
Cool. Thanks, Dominic. Great. So yeah, Ben, once Dominic gets you that code, all you have to do is hit run on this cell and everything should pop up just like you see here. Great. So once we have the system initialized, we can move on to time stepping. So like I said, what we're doing here is we're just setting the x velocity to 0.5 meters per second. So this is setting the 0 index, the 3 index, and the 6 index of this 9-element list to 0.5. And remember, the rest of them are zeros. So then what we want to do is we want to iterate for 5 time steps over the loop, and that's going to kind of move the system along in that given direction. So then we'll hit run on this cell, and you'll see that our fair lead tensions are printed out for us at the end of those 5 seconds as the kind of vector norm of the output forces that MoorDyn's returning at any given time step. And just one last step is MoorDyn closes the system afterwards, just to make sure we don't have any memory that's not accounted for. So you see, when we run this time stepping process, we produce some output files here. So we have this lines underscore line 1.out. And if you open this file, you'll see that it is the positions of all the given nodes in the mooring system as it kind of moves along. So that's kind of a useful tool for visualizing. You'll also see this lines.out file, and that's where those output channels are produced that we asked MoorDyn to produce. So this is where we see the fair lead tensions over the time. The last input file you'll see is the lines.log file. And so this is kind of where some more detailed information about what the mooring system is doing is printed too. Cool. So we have our output files. How do we visualize them? So to do that, we're going to use MoorPy. And a key to doing things with MoorPy is you need to have this line outputs flag P in your input file. So above, when we kind of set up our system, you can see that we put P in the line outputs, and that tells MoorDyn to print those positions. MoorPy is really straightforward to use. You have to create a mooring system, and you provide the following kind of inputs. You say, here's the file, here's the MoorDyn input file, here's the directory that it's in, here's the root name. So this is kind of this line's name that is appended to all the output files and the input file. And then you need to set this flag QS to 0. So that tells us that MoorPy is being used to look at MoorDyn outputs and not actually run any models. And then there's a Fortran flag, and that tells MoorPy what version of MoorDyn it's reading in. So Fortran false says, okay, we're working with the C code for MoorDyn. Once that's set up, all you got to do is call mooring system.plot, and that's going to give us our color. We can set our color to red, and then we can say the time that we want to output the system at. And so, okay, we're going to output our system at time equals 0, or the first time step. And when you execute that cell, you should get a nice little visualization that pops up that shows your mooring system with those catenary lines that we have simulated. Great. Okay. I'll kind of work through this next example relatively quickly as well, because there's not too much different other than we're using a body this time, and we're going to interface with the MoorDyn system just slightly differently. So yeah, we're going to be running the same system. We're going to have the 3 lines. They're going to be attached to the floating platform 70 meters below the water line. But to do this, we're going to use a coupled body instead of 3 coupled points. So this MoorDyn input file that I have pasted here is what you see in the body.txt file on your file explorer. You can see we have the same line properties before, but now we have this bodies section inside the MoorDyn input file. So we have a body, we're labeled it our first body. The attachment is coupled. And then we tell MoorDyn, where is this body located? Okay, we're going to say it's at x equals 0, y equals 0, and z equals -70, because that's where we're attaching our system. There's some other inputs you can have here. So R0, P0, and Y0 are the roll, pitch, and yaw, respectively. Tells the body how it's oriented at the initialization. The body can have mass, center of gravity, moment of inertia, volume, and then some hydrodynamic coefficients. Because we're just using the body as like a scaffolding for attaching mooring lines today, we're not going to deal with any of those. So then we get back down to our points list, and you can see it's very similar to the or to the previous points list, but now our fair leads are called body 1, or our attachment type for our fair leads is body 1. And so this tells MoorDyn that these points are attached to body number 1. You'll also notice that we defined our positions slightly differently. So we're still using the same x, y positions, and that's because our body is at x equals 0 and y equals 0. But our z positions are now 0. And that's because points are defined, or points attached to bodies are defined in the body's reference frame. So what we're saying is point 4 is 5.2 meters in the x direction away from the center of the body. And so the actual location of point 4 is the point 4's x position plus the body's x position. If you have orientations involved, it gets a little trickier. But that's just kind of a key point when you're using bodies, is you have to define in the body's reference frame if you have something attached to it. You see we have the same line list as before, so we don't need to review that. And we have the same options as before as well. And our outputs are also the same. So our first step is we're going to initialize our system. So very similar to how we did it before, but this time we're going to kind of use the MoorDyn functions that are available rather than doing it manually. So we create this MoorDyn system object, same way we did before. But now what we're going to do is we're going to get a body object from MoorDyn that it's created from the system. So we can say body object equals MoorDyn.getBody, and then pass MoorDyn the system object and the number of the body. So remember, we called this body 1 up here. So once we have our body object, we then can extract the initial state of the body. So this is the initial position and velocity of the body as defined in our MoorDyn input file. And we just say get body state, and then we pass the body object. From there, we can really easily construct our position and our velocity vectors just by changing these state values into a list. The reason we're changing them into a list is just because we want to be able to change them further on when we're working with our system. So once that's done, we initialize the system just like we did before, and you can execute the cell. So again, we can hit scrollable element, and then we can start looking through our outputs. So you'll see a lot of similar things. You'll see that we're reading the body.txt input file. Our log file is being written to body.log. You can look through the entities that MoorDyn's picked up on, and you'll note that now we have a coupled body where we didn't before, and we have one body as well there. It tells us, okay, we're putting the body at 0, 0, -70, and then it starts solving for the initial conditions the same way it did before as well. And you kind of get reports here of what MoorDyn's picking up on and what lines are set to. Again, it takes 52 seconds to solve. That's expected. We're running equivalent systems. So now that we're initialized, we can get into time stepping again. Time stepping here is very similar as to before. It's the exact same block of code. For extracting our fair lead tensions, I just used a slightly different approach that utilized these kind of MoorDyn functions a little more robustly than just the kind of more manual way from before. So we set up 3-point objects corresponding to the effective or the numbers of the points. So point 4, we call MoorDyn get point, and then system, and then the index of the point. And we do that for point 4, 5, and 6 because those are our fair lead points. And then to get the fair lead tension, we just take the vector norm of the point force, which is returned by the get point force function in MoorDyn. If we execute this, we'll see that our fair lead tensions that pop out here are the exact same as the fair lead tensions that we got from running the previous way when we had just coupled points and not the coupled body. So everything's working as it's expected. For visualizing, it's the exact same process as before. You just pass in your file name, your directory, and then your root name body. And yeah, you'll get this nice visual here and kind of be able to work with it. Just some closing notes. This kind of step-by-step process that I walk through here is the exact same way that MoorDyn works with OpenFast and how it works with WexSim. At each time step, we pass in those positions and velocities, and then we receive the forces back and are able to work with them. We're always looking for new projects to engage with, so there's couplings underway with Chrono and Hydrochrono, a bunch of commercial codes, and some other kind of non-public research codes that are also under development too. So with that, I'll wrap up this part of the demo. So this is kind of the end of running MoorDyn standalone. Before I move on, are there any questions? Cool. So let's see if CoCalc is going to kind of play along with this OpenFast demo that we're going to give. Okay, so back in the CoCalc world, back in our Visual Studio instance, we can move on to our OpenFast demonstration with MoorDyn. So if you move your cursor to the bottom of the screen here, you'll see that you kind of have this bar that highlights blue. And if you drag up on that, what's going to happen is you're going to open a terminal. And it should look something like this. You should have a little cursor here, and it should say like a ~/MoorDyn. So hopefully everyone is able to get there. So great. So from here, we're going to move into our MHK RM1 floating directory. And to do that, all we type is CD and then the name of our directory. So MHK floating or MHK RM1 floating and hit enter. And you'll see that our path now changed to say that we're in the MHK RM1 floating directory. If we type the command ls, that will list everything in our directory. And if we open the directory here, we'll see we have all of the same things. This is very similar to what Hannah worked on when she was presenting her OpenFast tutorial. I just made some slight changes that allow things to kind of run faster and more MoorDyn specific. So what we're going to be simulating here is the RM1 floating using MoorDyn, and this will be using OpenFast as well. So some things I just want to highlight is if you open your OpenFast input file, so the .fst file, and you scroll up to the top, you'll see that we have this comp mooring switch turned to 3. And that tells OpenFast that for modeling moorings, we are going to be using MoorDyn. So that's kind of a key part if you want to be using MoorDyn here. The other key part is that you give OpenFast the MoorDyn input file. So this mooring file flag, you have to provide the path of your MoorDyn input file. And you can see here, we have this file path, and it's the exact same file path as our file right here. For visualization with OpenFast, you can turn on some of these flags down here, and that will help you visualize the mooring lines. We're going to skip that for today because I think that might cause CoCalc to explode. So next, we're going to open the MoorDyn input file. So that's this file here, and we're going to look at our system that we have set up. So you can see we have one line type. Someone defined it up here and said it was chain, but all that's important is that you have your properties here. So we define our properties, we define the stiffness, our damping. Someone's given this a bending stiffness, and then we give it some hydrodynamic properties as well. I'm saying someone because these are the exact input files from the regression tests in OpenFast. So I didn't actually set these up, but these are kind of what we commonly point people to. Then we define our points. So let's see, we have 12 points here, and it looks like we have 6 anchor points and 6 fair lead points, and they are located. It looks like there's kind of 2 attachments to the actual device, right? So we have one that's at positive 34 and negative 10, and another attachment set of points that's at negative 34 and negative 10. This is a key thing to kind of highlight in MoorDyn. There's no object-to-object interaction, so you don't have to worry about placing things in the exact same location, which is really nice if you're trying to extract specifics for different systems. And then you can see our anchor points. There's 3 in the front, 3 in the back, and they seem to be spaced about 50 meters apart from each other. So you see we have 6 mooring lines. They're attached to their respective points. And so that kind of just shows us, okay, again, yeah, we have 6 mooring lines and 12 points. We have some solver options here. Not much to highlight other than MoorDyn F uses a different default initialization solver than the C code does. So this uses kind of dynamic relaxation where the C code uses static relaxation. And then we also have this out switch flag turned on. An out switch flag here just tells OpenFast that it doesn't need to print 2 copies of the outputs. It can just print them straight to the OpenFast output instead of also to a MoorDyn output file. And then you'll see here we have an output list as well. So those are the OpenFast, or those are the kind of input files we're going to be working with. Running OpenFast is super simple if things work as they should. So in our terminal here, we're going to type Anaconda 2023. And what that's going to do is turn on our Anaconda environments for us and kind of allow us to access those. So once that, does its thing and thinks through, you'll see that now Anaconda is activated and we have this little base here, and that tells us we're in our base environment. The next step is to activate our Anaconda environment for OpenFast. So we just say conda activate, and then we say OpenFast _env. And when that is successfully activated, you'll see that this says OpenFast env over here. So that tells us we're in our OpenFast environment. Once we're there, all we have to do is type OpenFast, and then we have to type the name of our OpenFast input file. So mhk rm1 loading.fst, and then we just hit enter, and our simulation starts. So you'll notice here that there's some different outputs printed to the console compared to when we're running the MoorDyn C code. That's just kind of how we have things set up between the different codes. But kind of while this runs, I'll just mention that you can also add a log file to the MoorDyn options here, and then you'll be able to see kind of the inner workings and make sure code's working as expected. So you see here.
What was that last command? Sorry.
Oh, sure. Yeah.
OpenFast what?
OpenFast space and then the file name mhk rm1 floating.fst.
Okay, thank you.
Yep. So MoorDyn right now is doing its dynamic relaxation process, and it's trying to initialize the system. You can see that things are running quite slow, and that's fine. It's just it's a complex, the whole setup here is pretty complex. So that's kind of why I wanted to kind of limit how quick things run. So you see here, after 5.5 seconds, MoorDyn converged. It reached the thresholds that we provided it, and then it says, okay, we're initialized. We can start our OpenFast simulation, and then OpenFast starts running. There's not much more to look at here. Once it successfully executes, we'll open up our output file and look at what's going on there. But yeah, that's effectively how you run OpenFast with MoorDyn. Again, I'll highlight this MoorDyn F example here that has kind of instructions on how to run the MoorDyn driver from OpenFast. It's a little bit beyond what we have time for today, but it is just kind of a nice example as well. So while we're waiting for this to finish, does anyone have any questions? Cool. So yeah, I'm sure yours probably might still be running. You don't need to wait for it to end. I mean, you'll see a message like this. It'll just say the amount of time that it took to compute, and then it'll say OpenFast terminated normally, and then I'll give you some messages here about whatever warnings or whatnot were passed from inside the code. You can see we don't have any MoorDyn warnings, so we're all good on our end. If we open up our .out file here, our mhk arm1 floating.out, this will give you all of the outputs of OpenFast. And if we scroll all the way over to the far right, we'll see that we have our output channels that we requested from MoorDyn. So this kind of file is not super helpful to look at because the columns don't line up exactly. But if you open it in a tool like PyDAT-View, things will pop up super nicely, and you'll be able to kind of look at how your MoorDyn system's behaving. Cool. So that kind of concludes our demo days on OpenFast and running standalone. So really quick, I'll just jump through how we run things with Wexim as well, because I think that's a useful exercise to go through. So to run MoorDyn with Wexim, I'm just going to give a screen sharing example and not use CoCalc because we have to use MATLAB and it's a bit complicated to get that all set up. So yeah, running MoorDyn with Wexim is pretty simple. The first you need 3 different repositories in your given space, and so you need this Wexim MoorDyn repository. You need your Wexim applications repository, and then you need your Wexim repository itself. And I've cloned all of those already into my MATLAB space here, so we can just skip that for now. So assuming that you have these repositories already downloaded, the steps to getting Wexim set up for running with MoorDyn are as follows. So you need to open up this MoorDyn folder here, and you need to open up Wexim, and then Wexim source, and then Wexim functions, and Wexim MoorDyn. What you need to do is copy the files from this MoorDyn directory into this other folder. And so what we're going to do is we're going to copy these top files here, put them into MoorDyn. We can replace the README. And then you're going to need to copy the MoorDyn library for your specific computer architecture. So I'm on a Mac that is an M series chip, so that means it has an ARM64 architecture. So I select these libraries. If you're on a Windows machine, you use DLL. There's a bunch of Linux libraries there as well, and then the Mac Intel libraries as well for older computers. So I copy those libraries over as well. So once I have those copied over, I can close this MoorDyn directory, and now I just need to open up Wexim, and I need to run add Wexim source. So that's going to make sure that Wexim is added to my path. and that I have access to it. So then we can go back to our kind of home directory, we can close that Wexim, we don't need that anymore. And we're going to go to Wexim applications, and then we're going to go to mooring, and then we're going to go to MoorDyn. And what we have here is a RM3 setup in Wexim, and it's set up to interface with MoorDyn. So before we get too far, I'll just talk through the Wexim input file, and I'll skip most of this because I think Mohammed and that Wexim team did a great job explaining things in their demo day. But I'll just scroll down to the mooring section here. So you need to have a mooring object in Wexim, and you need to define the input file path for MoorDyn using the MoorDyn input file here. And then you need to define that this is a MoorDyn system being run. It's not some other option. You say it has this many lines, this many nodes, and whatnot. And that's just more for visualization after the fact. It doesn't change how the simulation runs. And then you define the initial displacement of your object in MoorDyn. So you just say, okay, here's where it is located in space. So that's our Wexim input file, the changes that you need. Then for our MoorDyn input file, you'll see that we have a line type defined here as a chain. You'll see we have a coupled body, so we're working with one 6-degree of freedom coupling with Wexim, and that's required for any time you're running Wexim. You're only able to interface with a coupled body. You're able to have multiple coupled bodies, so you can simulate multiple Wex, but it does need to be a 6-degree of freedom interface. You can see we have our system set up here. Our points are attached to bodies, or they're fixed, or they're free. We have our lines set up, and then we have our solver options. So the one key thing to highlight in solver options here is this disable out time flag. So that's super useful for running in MATLAB, because MATLAB doesn't like to write things over in the console, so you can get kind of cluttered. So once we have both of those, all we have to do is type Wexim input file in our command. Let's see, Wexim input file. We need to execute that, so it initializes our simulation class, and then we just need to execute Wexim. And then it'll run, and you'll see pretty soon that you'll have some of the MoorDyn outputs that you're used to seeing as well pop up. So these are just kind of some Wexim console printing, nothing kind of super important to us for the MoorDyn specifics. And then you can see that MoorDyn closed, and our system ran, and then these nice windows pop up. So this is kind of how Wexim is able to show us MoorDyn output channels. So you can see that we requested FAIR 10, 4, 5, and 6, and so then Wexim reads the MoorDyn output files that are produced here, and then produces a nice plot of those. And you can see we kind of have these here, and we'll see our devices moving up and down and whatnot. So yeah, that's kind of the nitty-gritty on how you run with Wexim and how you run with OpenFast. I will just highlight for those who maybe felt like that was a bit much or a little too fast. We have some example PDFs here that just kind of talk through these steps of how to run things, and you can always go back through with the notebook as well and work on things there. Cool, and with that, I'll finish up the demo, and I think pass it back to Megan, I believe, for some from Next Notes.
Awesome. Good job, Ryan. That was super well done. I'm going to share my screen to close out this session. Oops. All right, can everyone see this? Yep, great. Okay, so we just heard from Ryan about MoorDyn today, May 7th. Our next demo will be 2 weeks from now on Wednesday, May 21st at noon Mountain Time, and this demo will also be utilizing CoCalc. If you didn't have CodeCalc set up today for Ryan's demo, make sure you have it set up for MHKit next week. And then we also have one more demo after that that will be using CodeCalc. So go into codecalc.com, create a professional or a personal CodeCalc account. It doesn't necessarily matter which one. We only just need your account email that you made your CodeCalc account with in order to add you to our Demo Days project. And from there, you'll have access to the course materials. So just some general housekeeping moving forward. Everyone did a great job today keeping their mics off during the presentation and demo. We can turn our cameras and mics on for the last part of this session as part of kind of a discussion and Q&A. Moving forward, you should have received an email with all of the meeting invitations. So please try to accept those meeting invites and add them to your calendar so that we can kind of have a head count. That just helps us know how many licenses of CodeCalc to distribute to student projects moving forward. That could be a huge help. Again, if you don't have your CodeCalc account set up, just email your username to Kelly, or the email you made the account with to Kelly, and then you'll be added to the Demo Days project. Awesome. And here's me and Dominic's email. You already had Kelly's on the previous slides, but if you have any issues regarding CodeCalc or any questions regarding the Demo Day series, just please reach out to us. Awesome. I'm going to stop sharing. So does anyone have any questions for Ryan or Demo Days in general? Oh, nice. Kelly just dropped something in chat saying to give her messages a thumbs up or thumbs down whether or not you used CodeCalc. That would be super helpful. Yeah, the floor is open. I have a couple of questions.
I was going to say I can start off with some questions.
All right, go ahead, Kelly.
Are there any specific instances or devices in which you think that MoorDyn would be useful or could work that are maybe currently overlooked?
Yeah, I think it is super useful when looking at, I think, some of the reference models and making sure that we're really accounting for mooring dynamics there. So I think that's a common case where people get really excited about the device and tend to overlook the mooring systems, not realizing, I think, that they can have pretty dramatic effects on the system. And using MoorDyn, I think, as a tool to help design the smallest mooring system possible can have some pretty dramatic cost impacts on the system and really help make it a more, I guess, realistic or real world system. I'd also say that any sort of like floating MHK turbine, if we are looking to kind of simulate how those currents are impacting our mooring lines and impacting the tensions, MoorDyn's a great tool for that as well.
Yeah, I think everyone would agree with this. Oh, Mohammed, go ahead.
Yeah, can MoorDyn generate the system metrics, then the simulation, or not?
What did you say the system metrics or matrix? And if you said matrix, what do you mean by that?
So in the WebSim, you can either define like MoorDyn, coupled with MoorDyn, or you can put a mooring matrix. And
yeah,
it is very handy, but when you are solving optimization problem that you need to run a model multiple times, MoorDyn takes time to initialize. So if it can somehow from the first few runs generate system matrix for the mooring system that you can just use in WebSim, to be much faster when it comes to optimization problems.
Yeah, there's a couple options on how to handle that. So No, MoorDyn does not create a mooring matrix, and that's because it's a dynamic mooring model, right? So it's not a static system. It doesn't produce a stiffness matrix per se. It actually determines, as the time evolves, how each point in the mooring system is moving under the loads it receives. So it does go into a lot more detail, and that's why it takes longer to run. So kind of as a design process, a lot of times what people will do is they'll use a quasi-static or a kind of a stiffness matrix for more systems to optimize their design. And then once they think they have an optimized design, they'll move on to doing a dynamic simulation using MoorDyn. So that's kind of like the second stage in the process. For Wexim, it's a little unique because Wexim is a dynamic solver itself. And so if you want to be using MoorDyn for that, what you can do is you can actually export your initial state of MoorDyn to a binary file. And then you can load in that initial state every time that you call MoorDyn. So instead of having to initialize MoorDyn, 50 times or 100 times or whatever you're doing your optimization for, you can just directly load in that pre-initialized state and go from there. Noting though that if you are changing your mooring system, you're going to have to reinitialize because it's going to have different properties.
Yeah, thank you.
I think there's a question in the chat as well.
Sure. Yeah, it's a good question, Ben. So we have a couple different ways we do this. We have a set of kind of pretty robust tests and regression tests that make sure that MoorDyn's behaving the same way it did before. But then generally any new big feature that we add, we have there's generally a paper that's published for that. So if you go into the MoorDyn documentation and you go to the references section, you'll see a bunch of papers that kind of list different features in MoorDyn. So we do either a validation study with experimental data, or we do some sort of verification work using a system that we know is supposed to behave a given way. So those are kind of our two main methods that we use for new features.
Thanks.
Yeah. That is a great question, Jason. No, there is no kind of object interactions or touching in MoorDyn. So yeah, there's no kind of knowledge if things are touching or colliding with each other. It would be a great feature to add in the future though, because I think in some of the cases where you're looking at line failures, you can have platforms that yaw like 180 degrees and your mooring lines can physically become wrapped up. And so it'd be good to simulate that in the future. Yeah, Kelly?
Yeah, I guess kind of a similar question to Jason's. What about if you have if like the anchor gets uprooted or if it drifts, moves, things like that? Are those cases that you can simulate in MoorDyn?
You can do that for sure. Not in the most direct way that you'd like to, I would say. But you can either simulate an anchor failure, so you can say, if the tension gets above this threshold, the anchor just breaks, and you'll have a line that's not attached anymore to the seabed. Or you can use controls, and you can say you're controlling basically the anchor point and lengthening the line that's attached to it. That can kind of be one way to simulate it. And then the third way is that you can just have your anchor point be a coupled point and just move the anchor point around as you want to. But as for like the actual mechanics of an anchor being dragged out and then dragged around, there's not a direct way to do that.
Yeah, interesting. Yeah, those are some interesting solutions on how to model those cases too. So thank you.
Yeah.
Any other questions for Ryan? No? All right. Well, thank you so much, Ryan, for the presentation and demo. I definitely learned a lot about MoorDyn, and you're so right that, moorings are kind of overlooked a lot of the time. So it's interesting to see MoorDyn's capabilities. All right, I guess we can close out this session. Hopefully we'll see you all at the next one, MH Kit, on May 21st.
Yep.
Great. Thank you.
Bye all.